In the last video, we looked at hypothesis testing, and we went through an example to try and build up some intuition. And I mentioned towards the end of the video that there were some details that we also needed to look at before we moved on. And so that's what I'm going to do in this video, is to run through another example of a hypothesis test, and that's going to bring up some of these other details that I mentioned. So in this example, instead of looking at toads and whether they are left or right-handed, we're looking at flowers and whether they are left or right-handed. And so our first step is to set up our null and alternative hypotheses. And our null hypothesis is that the population proportion of left-handed flowers is 0.25, and our alternative hypothesis is that our population proportion of left-handed flowers is not 0.25. Second step is to calculate our test statistic. So in this case, we've got a random sample of 27 flowers, and we observed 6 left-handed flowers, and so that's our test statistic. Third step is to calculate the p-value. So just like with the toads, I'm going to do a simulation so that we can calculate our p-value. So I'm going to set up a vector to store the results and then run 10,000 simulations, and in each one I'm going to sample flowers, a sample of 27 flowers, and the population proportion of left-handed flowers is 0.25 and of right-handed flowers is 0.75, and in this particular sample I got a right and then another right and then a left and then another right and so on. And overall, if I count the number of left-handed flowers in each sample, first sample I got 5, second one I got 4, third one I got 11, and so on. If we look at a histogram of that null distribution, this is what it looks like, and I can store those results in a frequency table. And then to get our p-value, we're looking at what we observed, which was 6 left-handed flowers, and anything more extreme than that, so 6 or 5 or 4 or 3 or 2 or 1 or 0. So if I add up these relative frequencies, it'll give me a probability, and then because we're doing a two-tailed test, we're going to multiply that probability by 2, and then that will give me a p-value. So in this case I get a p-value of 0.9306, and then step 4 is to make a decision. I compare this value with the significance level, and we'll use 0.05 as our significance level, and if 0.9306 was less than 0.05, I would reject the null in favor of the alternative, but in this case 0.9306 is not less than 0.05, so I cannot reject the null hypothesis in this case. So in this case, the data are suggesting that we cannot rule out the possibility that the population proportion of left-handed flowers is 0.25. So that brings up the first detail that I want to mention, and that is that you'll notice I did not say that this indicates that we've shown the population proportion is equal to 0.25. the population proportion of left-handed flowers. Okay, I cannot say that I accept the null hypothesis. All I'm allowed to say is that I cannot reject it. And you might think, well, I'm getting stuck on language here, but it's actually very important. And an analogous situation is in trials where the result of the trial is either the defendant is found guilty or not guilty. They're not found innocent. And it's a similar thing here. So rejecting the null hypothesis is like finding someone guilty, Failing to reject the null hypothesis is finding them not guilty, but we cannot say that they're innocent. And similarly, we cannot say that we accept the null hypothesis. So that's one important thing to remember about hypothesis testing, is that we can either reject the null hypothesis in favor of the alternative, or we can fail to reject it, but we cannot accept it. Okay, that brings us to the second detail that I want to mention, and that is that every time we do a hypothesis test, we can actually make an error. And I don't mean an error in the sense of making a calculation error. I mean an error because that's the nature of hypothesis testing, is that we are using a balance of probabilities to make a decision, and so it's possible that the decision we're making is incorrect. And there's two ways in which we can make an incorrect decision. So first of all, let's think about the toad example from the last video, where we ended up with a really small p-value. I think it was 0.03 something. It was smaller than the significance level 0.05, and so we rejected the null hypothesis in favor of the alternative. But what if that null hypothesis had been true? If that was the case, by saying that we reject the null hypothesis, we would have made a mistake. That's called a type 1 error. So a type 1 error is incorrectly rejecting a true null hypothesis. What's the probability of making a type 1 error? Well, it turns out it's the significance level. That's the definition of the significance level. So I'll just let that sink in for a second. So if incorrectly rejecting a true null hypothesis leads to a type 1 error, and we can control the probability of doing that by setting the significance level, presumably we don't want to make an error, so why not just make that significance level even smaller? Then the chances of us making a type 1 error is going to be reduced, and surely that's a good thing. Well, hold on. Trouble is, reducing the significance level increases the chance of making the other type of error, which imaginatively enough is called a type 2 error. So what is a type 2 error? So a type 2 error is when we incorrectly fail to reject a false null hypothesis. So if we think about the flowers example, we failed to reject the null hypothesis there. But what if that null hypothesis was false? So we should have rejected it, but we failed to reject it. So again, we've made a mistake, and that's a type 2 error. And the trouble is, there's a trade-off here. When we make the significance level too low, we end up increasing the chance of making a type 2 error. And so you can't set it too low. And so the balance that tends to work reasonably well is to set the significance level at 0.05. And that tends to make the chance of making a type 2 error not too high. There's another piece of terminology here that gets used in this context, and that's the power of a hypothesis test. And the power of a test is the probability of correctly rejecting a false null hypothesis. So in other words, it's 1 minus the probability of a type 2 error. And so ideally, we want to have a test with high power and a low probability of a type 1 error. So we set the significance level low to make the probability of a type 1 error low, and we use tests that have been demonstrated to have high power, and that reduces the chance of making a type 2 error. So that's how all this all works together. Okay, so there's quite a few things to wrap your head around with hypothesis testing, and so I hope these last two videos have given you a little bit more of a feel for the intuition that underlies hypothesis testing. As we move through the rest of the course, we'll use hypothesis testing a great deal, and so as I mentioned before, laying out those 4 steps is going to be critical to keeping things manageable. And so in the next series of videos, so the videos for each lesson, I'll be running through many hypotheses tests, and in each one I'll lay out those 4 steps clearly. So stating the hypotheses, calculating the test statistic, calculating the p-value for the test, and then making a decision and drawing a conclusion.